Bonjour à tous, c'est un grand plaisir, un honneur du coup de prendre ce poste voilà, au débeauté pour présenter Andreas Bikfalvi. Donc Andreas en fait c'est quelqu'un, alors merci le profil ChatGPT que j'ai lu, que tu m'as envoyé sur
Ah
WhatsApp, ça
ouais.
me permet de résumer vraiment ta carrière. Donc Andreas en fait a maintenant un triple diplôme. Il a un diplôme de docteur en médecine, puis un diplôme de docteur en biologie, biologie
Science.
notamment endothéliale et
Science.
maintenant ouais, en sciences exactement, et un doctorat maintenant en philosophie avec l'université de Sorbonne. Donc c'est un parcours original, particulier. Ça permet aussi de réfléchir un peu autrement, de voir la science autrement. C'est vrai qu'on a aussi d'autres équipes sur Bordeaux qui voient aussi ces types de problématiques scientifiques à travers le prisme philosophique. Et voilà, alors moi, je suis évidemment, historiquement, je suis passé chez toi, Andreas. Donc j'ai pu travailler la biologie vasculaire avec toi. Et aussi,
Pas
c'était
uniquement
au
la
tout
biologie
début, pas
vasculaire,
que, pas que. Et le glioblastome
le
à fond.
restaurant.
Ouais, ouais, tout à fait. Et c'était tes tout premiers pas en philosophie. Donc on philosophait dans le bureau, évidemment, comme on a pu connaître tous plus ou moins lors de réunions intenses. Je pense que c'est ça, il y en a plein qui sont passés dans l'équipe. Et voilà, donc Andreas, on va être vraiment content d'écouter ce que tu vas nous présenter sur la complexité de la causalité du cancer. Et floor is yours, because now we need to speak in English, right?
Yes.
Thanks.
Okay. So, so in fact, so I will speak in English now, and the work that I will present now is related to a conceptual analysis of cancer. So I did this work in the frame of a PhD at the Sorbonne University. And it's quite interesting because at my age to do a PhD, it's a little bit strange, but I mean, philosophy is so interesting, and the link to cancer so important that so that in fact I had to do that. So I will start now with the complexity of cancer and a scientific and philosophical investigation. So what will be the outline of my talk? First, I will talk about causality and the general considerations and challenges for cancer. Then I will, sorry, how is how I do that? Okay, good. So then I will talk about the theoretical concepts, so cancer frameworks of cancer that are focused either on the tumor cell or focused on the tumor microenvironment. Third, I will talk about theory of causality and their importance for the interaction between the tumor cells and the tumor microenvironment. Then I will present some case studies, which are diffuse gliomas and kidney cancer. And at the end, I will summarize and discuss a little bit and do also conclusion. So, general consideration, first of all, there is the problem of causality. And the second is also the problem of causality and its connections with cancer. So, understanding causality. It's the why question, in fact. It's the why question, why things are as they are and why things are changed with time or under the influence of some effects. And there has been a debate in science and in the empirical tradition. The empirical tradition always said that the why question is not acceptable. They are metaphysical, and in fact, they explain a kind of causal fundamentalism. However, the how and why questions are really strongly connected, in fact. First of all, for instance, you have B is transformed in B star. And you will ask, why is B transformed in B star? And the second question is how B is transformed in B star. That means the A, so you will also will identify the A that will do the job. So there have been some schools that were really against causality. And these were, for instance, Ernst Mach, Ludwig Wittgenstein, Bertrand Russell, and more recently, John D. Norton. For Bertrand Russell, all philosophers of every school imagine that causation is one of the fundamental actions, postulates of science. The reason why physics has ceased to look for causes is that, in fact, there's no such things. And the second, John D. Norton, more recently, causal talk amounts a little more than an earnest hymn of praise to some imaginary idol. It gives great comfort to believers, but it calls up no force or power. So causality for these people is a kind of folk science and has no real place in science. Okay, next. There's a second school that's in fact was against causality, and these are statisticians. And these people are from the frequentist school, except Francis Galton, who a little bit was thinking of causality, but at least Karl Persson and Ronald Fisher, they were strongly against it. Because the problem is that causality is a claim that you have one factor that acts in fact on the other, and the stuff is not reversible. But there has been some heretics coming out, and one of them was Subal Wright. Subal Wright in the 20s, he proposed what has been called the path analysis. So the Subal Wright was a geneticist, and the path analysis was in fact how several factors, genetic factors, development factors, and chance are interfering and acting. And he, of course, this requires probabilities that are related to these factors. And so he could determine how much of so how much probability is associated to the genetics or the development and so on. So then so this was a whole evolution with Persson, Fisher, Galton, Wright, Subal Wright, who really identified path analysis. And of course, there's been a lot of controversies going on with Niles, who was against path analysis and causality. But at the end, it came to the fact that Judah Pearl, who is the major proponent of causality, who has published his fundamental book, Causality, in 2000. And causality, now we have a causal revolution, in fact, going on. And this is also related to artificial intelligence and so on. So this is Judah Pearl. And for Judah Pearl, in fact, there are three stages. There's the association, there's the intervention, and the counterfactuals. So the association is what normal people in general do. So it's in terms of statistics. So the statistics stays at the association level. Then you have the intervention level and the counterfactual. So the intervention means that you modify a factor, for instance, X, you act on X and you look what's happening to Y. And the counterfactual is what if I had not done. That means if the factor is absent. So it's in fact correlation. Then Pearl identified the do operator, which is do X which will have the effect on y, so with the probability. And there's the potential outcome when x is absent. So I recommend the book of Y of Judah Pearl. It's pretty easy to read. It's a good read, and you will understand more about all this. Now, understanding causality in the context of cancer. So you have external causal elements that including the exposome or treatments. You have internal organismal factors or conditions, such as age, performance status, and comorbidities. And then you have internal tumor-related factors that are subtype, that is the baseline tumor burden, and the extent of resection of tumors. Then you have internal processes which involve cellular and molecular interactions as well as regulation with these interactions. And so you see on the left that you have in fact the IOF, that means the internal organism factors, and the ITF, that means the internal factors are situations and conditions that will act on the causal relationship. And these causal relationships are in fact on the left. Of course, you have the external causal factors like the exposome or the treatments. And then you have also the internal processes which are in fact also causal chains. And the focus was mainly on these internal factors. So there's one other notion that has to be introduced. This is called non-reductionistic physicalism. So this means that you have a strata of investigations. For instance, you have phenotypes, you have genotypes, you have translation, you have proteins, and so on. And so what is non-reductionistic, that you cannot reduce fully one layer to the other. And you have to so how do you say, to mix the two things all together, because they are in fact, if you want to understand the process, a cellular process, a general process in development and so on, you must be, of course, non-reductionistic physicalist. So this is very important. Now, the internal processes are related to the tumor cells and the tumor microenvironment. And of course, the tumor microenvironment is extremely complex. There's the tumor cells that are producing a lot of factors. There are promoting factors, attracting factors. There are autocrine loops. There's also the interaction with the tumor microenvironment, because the tumor microenvironment is recruited by the tumor cells and has an effect on the tumor development. However, the understanding of all this is really complex, and people often will only go for one factor or a few factors, even if they have done, for instance, large screenings and so on. And so often you end up with your favorite factor which will work. And of course, this gives, when you have all the data for several labs, they're working on this, they're working on this, and often also you have data that are contradicting each other. And this creates an understanding that is blurred. It's like a cubic picture a little bit that we see here. You see, so we have we see a little bit the faces and so on, but we do not understand really what's going on. So general theories and conceptual frameworks of cancer. focused on the tumor cell or on the tumor microenvironment. Now, there's one general framework which is represented by the hallmarks of cancer. So the hallmarks of cancer has been proposed by Doug Hanahan and Robert Weinberg. And I think there's been recently a new one out there. But here I depicted the three first. So what you see clearly that you have an enrichment of characteristics of hallmarks that are signaling a dependence on the TME and an enrichment also on the signaling that are signaling, so a dependence on metabolism, on epigenetics, on plasticity, on senescence, cell death, and so on. So it's a complexification function of time. So what are, in fact, the limitations of these hallmarks? Okay, the hallmarks is a kind of framework that's is adapted for the conceptualization of cancer. It's fairly complete. It's a mapping of all the interactions that are occurring in terms of cellular and molecular interaction, but there's a big but, that this is descriptive mainly and non-causal. So this is one limitation. Then it has a really heuristic limitation that means that the characteristics are assembled in a really independent way, and this independent way will so in fact lack of cohesion. Then there's underlying molecular evidence, and the explanatory power is also limited because it's often redundant. It lacks specificity. For instance, you have the MAP kinase pathways doing all kinds of things, not only one, many things, and you don't know exactly the switches that are in fact going on to drive one or the other phenotype. Then there's absence of dynamic interactions, and there is the distinction of characteristics and hallmarks is blurred. So the second overreaching causal framework is what we call the SMT versus the TOF. So SMT is somatic mutations theory, is the classical one, and the TOF is the tissue organizing field theory. So there are, in fact, the SMT states that cancer is caused by genetic mutations in individual cells leading to their transformation. So this is the hard SMT, and the top suggests that cancer cells mainly result from a disruption of the tissue microenvironment and the surrounding cells. So what we have here is when you look on the SMT, so the initial event occurs at the tumor level, it's genetic. Quiescence, cellular quiescence is an intrinsic state, and the disease is not reversible. The model is linear and lacks of feedback control. So the second, the initial, in fact, event is the disorganization of the tissue. It is claimed that the intrinsic state of the cells is proliferation, and the disease is reversible. So both of these have limitations, strong limitation and criticism, because it's in fact a mix, what is really truth. And I have formulated 4 substructures. So the classical SMT, strong SMT on the left, and the TME, so the TOF is on the right. And then you have, for the strong SMT, you have mutations driver, you have non-competitive activation, competitive activation, of the tumor cells, I speak, because there's the work of Phil Jones, for instance. So the work of Phil Jones is important because he did all these studies about the competition and non-competition, so the elimination of clones and so on. So I have formalized this also here below with some equations. Then you have the second is the hallmarks. So here the probability of tumor formation, genetics, regulation, and the tumor microenvironment are to some extent really intertwined. Here you have also the formulation in probability, and then you have the moderated TME, where is shifts is even more to the right. And then you have the strong TME, which is the tough effect. That is the probability of the tumor formation is essentially dependent on the tissue interactions and not on genetics. Okay, so this is just quickly. So now the third part, philosophical theories of causality and their relevance to the interaction between tumor cells and the tumor microenvironment. So there are a lot of philosophical theories. There's the regulatory theory, there's modulatory, counterfactual, probabilistic, interventionist, inference of the best explanation, causal pi model, Granger causality, singularist theories, and situation-specific and critical theories. So there you have all this, and when you start to go into the field, it's like a shock, it's a shell shock. So you have to understand, because it's another way to think, in fact. So, in fact, you can divide these theories into two groups. What is causality? So they want to know what is causality. And the second is how to determine, model, and apply causation. So there are two things, and they are also to some extent intertwined. But in fact, there are these two aspects that are really important. So the first one is the classical one, which is the Humean regulatory theory. We have no other notion of causes and effects than that of certain objects which have always been conjoined and which in all past cases have proven inseparable. So the formulation is below. But what is important in the regulatory theory is only the occurrence of regulatory events. It's not claiming there's a physical interaction. It's just a habit of the mind, in fact, which identifies these regularities. It's in fact, in this case, a mental construct. Then you have the causal inference, which is related to that of John Stuart Mill. So John Stuart Mill, if one time an event takes place and another time it does not take place, and all the conditions are in common except the one, which exists only in the first event, the condition which is different between these two events is the cause, or an indispensable part of the cause of the observed phenomenon. So for Mill, he has in fact two things. One are the causal factors. It's no longer working. So one, get this away here. So one is one are in fact the causal factors. So which is the C1 to Cn, and the other are the events that negatively will affect the causation. So we have the C1 and Cn, and you have the D1 and the Dn, in fact. And the events are contiguous to E in the spatial temporal sense, provided that the events D1 and Dn are absent. So this is important. So what we call confounding factors now. So the confounding have to be absent. So this is the causal inference. Then you have the probabilistic theories, the SEM, that means structural equation models, structural causal models, and structural situation-specific causal models. So you have here the theory. In fact, there are two persons who are really important in this respect. There's Judah Pearl and Nancy Cartwright. So Judah Pearl, so they have proposed this kind of DAGs, which are in fact represented by directed acyclic graphs that you see here in the middle. So this is not good here. So that you see here in the middle, okay? So you have x1, x4, and they are connected by path coefficients, which is the beta 1, beta 2, and so forth. And that converges to y, which is the endpoint. And then you have these DAGs have properties. So they can either have forks, which is the fork structure that you have a Z that is acting on the X and the Y. Then you have chain structure that you have X, Z, and Y following, and they have collider structure. That means X and Y are converging to Z. And all this, of course, raises problems because you may have confounding factors here, and you have spurious correlations. That means, for instance, when you control for Z in a collider, you may have, in fact, thinking a correlation between X and Y, which is not really true. Okay, so there are what they call backdoor criterions, collider, front door, and so on. So I won't go into these details, but at least you know a little bit of this. So the second is the interventionist theory of causality of James Woodward. He's a philosopher. So in this theory is when you do X, so the probability when you do X, when you act on X to have Y, then so this probability is different than the probability when you do on X, how do you say, prime, and you have Y. That means your probability is related really to the action of this specific X. So the causality from X to Y corresponds to the sensitivity of Y to a forced change of X, while keeping other factors constant in a given context. So you can see this in the formula below. So the other factors are B, so it's the background. And when you keep the background so constant, you have X causes Y. So with that formula. So that's the way it goes here. Then you have the counterfactual causality. So the counterfactual causality is the last step of the causal ladder of Judah Pearl. So this is in fact, this is also a philosopher who's already dead. It's called David Lewis. And so we can express the counterfactual as a relation between two variables expressed as P star acting on Q star, given that P is absent. That means that you have P star is the unrealized antecedent of Q star, and the consequence depend on P star and So in the condition that you do not have P, okay? So you have P is in fact absent of the of the real world. So in the real world, it will not occur, okay? And this means that at the end, you have in fact theory that is important when you add the do operator and the counterfactual. And these are the two criteria which are important for determining a causal relationship. And there's just a singulars theory, it's just for fun. I do this. So in the singulars theory, there is a physical interaction between things. So this is done by Phil Daub, who in fact went further than Salmon, who did the Mark transmission theory. And so there's processes, the interacting regions, quantities, currents. There's kind of hyperspace. So he formulated this in a really abstract way. And then there are the Inus conditions, which are in fact insufficient but necessary part of an unnecessary but sufficient condition. So this is so you have to be so you have to know first what is the sufficient condition cause in fact. So C1 is a sufficient condition when you have C1 or C2, okay? Or that means each of those are sufficient condition to E. So to produce E. C1 is a necessary cause if it's only acting together with something else. That means C1 and C2. So these signs, the other is or, goes like this, and the end is like it goes like this. And if you have a necessary and sufficient condition, it's just C1 acts on E. And then you have, of course, the Inus conditions, which is in fact what you see here below in this formula, that you have C1 and C2, or D1 and D2, that will in fact produce E. That means you have two necessary conditions that are in fact embedded in sufficient causes. You see that? And you can have a long chain like this. So it's an interesting concept because there's a lot of philosophical theories. Problem is how to apply them to cancer. And the useful in our context is the interventionism and the counterfactual. These are the dark, the SEM, the SCEM, the SCEM, the do operator, and the situation specificity, and also the Inus conditions. So these are the work horses of causality, which may be useful for cancer. Just an example. Here's a directed acyclic graph and a structural equation model. So I have done it simple, it's just an example on the angiogenesis VEGF because we know this pretty well. It's a pretty simple way. So one, you have the tumor cell secretion VEGF. You have VEGF binds to the receptor, activation of the receptor. Then you have intracellular signaling. Then you have angiogenesis and tumor development. So you have this type of sequence. Okay, so it's a sequence, and all these things. This is a linear sequence here. It's not really branched a lot, except you have when you have the angiogenesis down, you have more VEGF produced, in fact, in the tumor. And you can formulate this with this type of equations, where you have the beta are the part coefficients, Okay, so for each interactions, the epsilon is the noise, in fact. So you have each time when you have when you have an interaction, you have noise, and you can have then at the end, so you can map this in a full line here. And of course, this is related to probabilities, okay, of occurrence. And then you can also apply weight on each of those. So which has been named alpha. So you have the beta is the path coefficient, and the alpha is the weight of each variable. Okay, so now the second is the SCAM and the SCEM. So it's much here. What we have clearly is the infusion of the do operator in the counterfactual. Okay? So you have here, so when you, so here you have the do operator in the counterfactual because you can put VEGF at zero, the receptor at zero, which is a counterfactual, and then you will have the probability that is going, so what is going on, and you have also the noise and exogenous factors that are the UV, UR, URA, UA, and UG. And the second is the situation-specific causal equation model. So the situation-specific causal equation model, it takes into account the supporting factors. You can have a lot of supporting factors that are S1, S2, S3, S4, S5, and so on. I have illustrated this like this. So you have the causal chain, that is this one here, and then you have the supporting factors. The S, for instance, if you have endothelial cells that are viable, if you have an adequate expression of the VEGF receptors, if you have the metabolic conditions are okay, and if you have so a low level of endogenous inhibitors. So that's the way. So then you have a lot of additional properties of this causal frameworks. It is stability, pluralism, granular specificity, hierarchy, and so on, which I've put here on this slide just to assemble those. And more in detail, it's so the additional characteristics. So what we have, in fact, is the validation of the causal structure, which can be done by the DAGs and by these equations. You can identify confounders, colliders, confounder bias, collider bias. You have the SEM, SCAM, and so on. And you have dependent, independent, and instrumental variables, the do operator, counterfactual, and mediators. Then the other is also causal stability. So for instance, in this example, you have VEGF here and angiogenesis. VEGF1, angiogenesis 1 in the context when you have matrix, when you have stroma and so forth there, which is stable, and then you change just VEGF to zero. That means you do a counterfactual. So when you do this counterfactual, then you can see that stability of the causal relationship only exists when you have the VEGF there. And there's also, so the time factor, I won't go into the details now because it will be too time consuming. But so the time factor is very important, and you can map this also. Then you have the spatial dimension, and then you have the Innes conditions, which are, for instance, the Innes conditions You can have, for instance, so map the Ines conditions on angiogenesis or on invasion. Then you have an angiogenesis module and invasion models, and it's in fact then Ines conditions. And then you have the domination also, where you can so identify in a network the variables that are in fact more important than the others. Okay, so I just go, and this is just for curiosity, an example where I've mapped the Fildau theory of so his theory where the quantity are conserved on so on this interaction on hypoxia VEGF, angiogenesis, and tumor expansion. So I won't go into the details, it would be too long. Now, case studies. So in my work, I have done also case studies on two tumor types, on the IDH wild type and IDH mutated gliomas, and on clear cell renal carcinoma, because these are the main tumors where we have been working on in the lab. So diffuse gliomas, you have two subtypes, which are, let's say, in the adult. I don't speak so about the others, infantile gliomas. There are two subtypes, the IDH isocitrate decidrogenase wild type and the mutated form. So they have a local regional expansion and strong tumor microenvironment interactions. So you see that there's a lot of other mutations associated on these two types. Once the IDH wild type, you have the third mutation, loss of chromosome 1. And this is the classical glioblastoma. And then you have the mutant, where you have the astrocytoma and the oligodendroglioma, which are characterized also by specific mutations. So when you do the causal analysis here, so I've put processes only into a program that is called DAGITI. So this program is very easy, which allows you to see if your causal graph is okay. So your causal graph is okay. So it gives you that you have no open vectors or paths, and no correction is needed, in fact, to estimate the total effect. So what you have here, you have the angiogenesis modules, you have the invasion modules, you have the expansion of the tumor mass, you have the oxidative state, you have adaptive immunity, glycolytic state of the tumor cells, and so on. And this can then be mapped like this. So you have for each of those, you have path coefficients. So you have, for instance, the oxidative state, you have a path coefficient to invasion for the neural input, you have a path coefficient invasion, and so on for angiogenesis, and so forth. And you can do the same thing with IDH mutated gliomas, but what is the characteristic of the IDH mutated gliomas is that you have really shut down or really slowing down of the angiogenesis part on here, or which is on the left, and also the adaptive immunity. So these are really down, so the probabilities are nearly zero there, and it's mainly through the invasion, some innate immunity to the neural input that is in fact progressing. And you see here the wild type is that so on the right side you have an active growth here with the plateau, and this when the plateau is reached, the patient is dead, and the IDH mutant is in fact, there's a lag phase, a long lag phase, very diffused, and then suddenly so it's active. That means at that stage, the angiogenesis and all the other stuff is coming in again. Okay. So then you can formalize this, and you can do also the interference here. So these are some of the these are the equations for angiogenesis, tumor-derived angiogenesis factors. So the tumor mass expansion. So I have done something here. I have introduced the do operator here. So when I change, for instance, the adaptive immunity, I act on the, or if I act on invasion, or if I act on the oxidative, and so on. So I have, so I've applied a do operator here, which then gives you a causal, really a causal link. Okay. So the other way to look on this is to do a reductionist causal analysis. So you define two states that is in fact compaction, diffusion, and invasion. Okay. In the IDH wild type, you have so an ongoing thing like this, which is invasion, compaction, and that it's at the end it will plateau. And for the IDH mutant, you have this lag phase, and then starts the sequence after a long time. So this sequence, so the compaction and diffusion are of course dependent on a number of factors. For instance, compaction, neuroangiogenesis, so astrocytic activation, the matrix, anti-invasive effects, internal glycolysis, and so on, hypoxia. And in fact, for the diffusion, it's the same. You have external and internal factors. So you can formalize this. So in my work, I've done a lot of these. This is just an example. So you can in fact define the probabilities that you have for the compaction and for the diffusion. And for instance, when you switch from compaction to diffusion, then you have a transition, a state transition, okay? Which means that you go from the compaction to diffusion. And then you can have the other one from the, so state transition from the diffusion to the compaction. And the variable, you can add these equations, the OXPHOS and so on, the migration, the matrix, when you go from the compaction probability to the diffusion. And you can do exactly the same way in the, so in the other sense. So the thing is that you can so expand this a lot with so a lot of factors. And what you have in fact, so you can map this like this with the probabilities. So you have sequence of probabilities. So you can have a simulation here. I did only the simulation where I've associated the OXPHOS and the glycolysis. Okay. So you see clearly that when you have the glycolysis, so when the XPHOS is going up, then you have an increase in diffusion, and when then the glycolysis goes down, and when the glycolysis goes up, you have an increase of compaction, and this repeats in alternative cycles. So then you have other models, but I don't show them now. Now the other thing is that the thrombospondin thing. So the thrombospondin I've done also. So on this, the model, I put this the same way in the DAGIT to see if the interactions are okay. As you see at the right side. So this is the work of Tom, who was at that time in the lab. And so you see here, so in fact, I've mapped all the interactions here. So then you can so of course, put this in equation form here. So with the, so I won't go into the details. To be, so what time is it now? Okay, so I have to hurry up a little bit. So so and then you can in fact identify the sequence. And here in this, I have also added the alpha variable and the beta one. Okay, so the beta is the path coefficient, and the alpha is the weight of each variable. And then you have dominance conditions. So you can define them like this. You may have TGF beta is more than hypoxia, or hypoxia is more stringent than TGF beta. TGF beta and hypoxia are the same. CD47 is acting higher or more than CD30. And you have also the inverse. And this you can map all this on path coefficients. Okay, so in your DAG. So now the other thing is renal cell carcinoma. I've done a similar approach to renal cell carcinoma. So renal cell carcinoma, as you know, it's let's say the most common form of is the clear cell renal cell carcinoma. And so the general scheme is VHL loss, HIF degradation pathway silence, HIF accumulation, VEGF is accumulated more, acts, and is also effects on tumor cell metabolism, on chemokines and immune regulations. So here the same, I've done the formalization of these interactions with the scheme here of Judah Pearl. I will go quicker. And then the IL-34 immune modulation and tumor impact. So this also, I did the model. I put this also in the DAGIT here, and the result was okay. And then I mapped these with these equations that are shown here. And then I can also use interference, for instance, treatments, responses, and so on, to see how this tag is changed and the probabilities are changed. Okay, so summary. So what I've done here is I've given a general introduction of the problematic of causality. I have criticized the hallmarks and SMT in the top. I have done, in fact, a description of the philosophical theories and a link to cancer. And then I have done case studies on gliomas, on diffuse gliomas and renal cell carcinoma. And in fact, the open questions is the impact of all this. So the contribution and practical implication. First, attempt to conceptual unification of causality in the tumor microenvironment. So provides a framework to assess the coherence and quality of causal networks in cancer. So offers a perspective, a new way of classify tumors, I hope so. May promote development of personalized therapeutic strategies that are in fact related to dominance factors in the causal chain, and may eventually guide research to explanatory models. So, okay, so I won't go into detail here, but this is just a short summary. That is, in fact, the So I did the conceptualization of the TME with the tumor cells. I criticized the hallmarks and the existing frameworks. Then I realized an interdisciplinary research where I used philosophical concepts and scientific ones and tried to merge them, and so on. So these are the main things that I've got. So there are a number of questions. Is causal modeling only descriptive or allows it to clarify concepts? Does this have an impact of cancer research? The causal sequence is it linear, branched, or circular? What is the level of organization, non-reductionistic physicalism? Modeling cancer, is it simplifying or complexifying? What is the connections between causes, conditions, and background? How modeling can guide medical practice and how the understanding of causal structure allows the formulation of interventions. So this we can discuss, and what is really to see that there's a triad that is important, which is the correlation, the do operator, and the potential outcome. Okay, so these are the three that are really important to have a causal understanding of things that are going on. And I refer again to the Pearl, the book of Why. You should read it. So thanks to all people from my former unit that have contributed to the experimental work, and team one of the BRIC, of course, then also the IHPST and the Doctoral School of Philosophy in Paris, and my PhD supervisors and colleagues for inspiration and discussions. Thank you very much.
Is there any question? Can I ask one?
Yeah, you can.
Yes. Okay, thank you, Andreas. Very interesting. Sometimes it's concepts which are sometimes difficult. I was wondering, with your multiple background, is this work on philosophy, and I mean, you gave concrete examples. Did it change something to your view on scientific topics? You know, what you're developing in the lab in parallel? You know what I mean?
Yes.
To take the problem from another direction than what you were thinking before.
Yes, I mean, the thing is that you have two ways to deal with this. You have the interaction of philosophy with science and the effect of science on philosophy. So you have this, let's say, the two way to think. Now, for the first one, for the effect of philosophy, so on science, it's you have some of the questions that you have that scientists are formulating can be in fact recontextualized in philosophical language. Okay, so that what in fact I've done here, because I've used the concept of causality. So to do that, which is in fact from the basis of philosophical concept, it comes also from artificial intelligence and so on, because now it's in vogue with the LLM and all this. But so this is one thing. So my thinking, of course, has evolved, because I would prefer to go more on big questions now, you know, on, I mean, what we call the alimentary science. So this I don't. So I want really to dig into really the fundamental questions, and maybe this way to think will help us to
So to address it and then to understand also the complexity better, because the problem is really complexity. And the other thing is also that this, when you look on the causal relationships in the scientific field, then you can really also teach the philosophers how to think, what you can apply in the philosophical thinking, and what you cannot do. Because the number of things you cannot do just so it will be on the moon, you know, like so this is the way in fact I see it.
The equation you propose are formal equations.
Yes.
Can you put values on the alpha, beta, etc.?
You can put, yes.
And and are these values general values or patient dependent, tumor dependent? How they can help for treatment of?
So what you can do is first you can do simulations. That means that what I've done in my work. So I've done simulations where you have, for instance, chosen some of the beta values, some of the alpha, and so on, and to get in fact a score. You know, when you so for instance for so what was so when you have, for instance, the effect on tumor development. In fact, so I've calculated when you act only on let's say on the angiogenesis part, and when you act on the invasion part. So when you act on the invasion part alone, so the average probability is pretty low, or it's not. I mean, it's lower than the other ones. When you act on angiogenesis, the probability is a little bit higher. But when you act on both in the invasion and angiogenesis, you have really a much higher probability. So this is one thing you can do. So you can simulations. The other thing you can do is to look on experimental data. The experimental data is somehow a little bit tricky because often you have an integrated system, and you cannot from an integrated system to transpose this from an in vitro system is more difficult. What you can do is to look on also clinical data, on transcriptomic data, and interfere in an indirect way what's going on, even though it's not so simple, okay? But you can use that for the inference. So what I've done also, so I've done, for instance, on the thrombospondin thing. So I've done exactly that. I've looked up the data and shown in fact that so when you close the back doors in this data, the probability is pretty high that the thrombospondin and the thrombospondin pathway is really acting. So that you can do, but of course the problem is then I hope with this new technologies like with the proteomic, the single cell, the spatial transcriptomic, the all kinds of stuff, it can even enrich all this. It can make it more complex, and that's the way to go. And also the organoids structure, when you have more integrated structures, when these systems are really working, then you can much easier validate the probabilities that you have. Yeah. So that's the of course the critical problem is the experimental validation. So in the real world, that's the stuff, and we need to do work on that.
Just a last question. You referred to many philosophers.
Uh-huh.
Based on the names, I think there were many Europeans and or Americans. It's a bit provocative question, but if you discuss with Asian people or African people, do they have the same concept of what you were talking about?
I mean, the causality and in fact the science that we understand as science is in fact a Western invention. Yes. Okay, so but the for instance Asians, they have the same. I mean, you know, in the causal, there's a lot of people in the causal domain, also in the philosophical domain, that are Asians. I mean, from Japan, some from Korea, some from all kinds of, and they adhere to the same thing. Of course, the thing is that science and philosophy, at least scientific philosophy, not the what we call the non-scientific philosophy, because you have the continental philosophy, which is more Heidegger, Hegel, and so on. I mean, all the classical ones. But there, and then you have the more, they were initially not Anglo-Saxon, but they became Anglo-Saxon, was the, in fact, German from Vienna, so the Vienna Circle and the, so all kinds of people that in fact moved afterward to the States and did this, so this kind of more analytical philosophy. So I'm more in this scientific philosophy thing and not in the Heidegger stuff. Even that I'm reading now Heidegger again, but it's very difficult to understand because they have invented artificial languages that are in fact not precise concepts. So you have to imagine what the guy is saying. So you project your own imaginations. In fact.
Any other questions? Okay, thank you again, Andreas.